Welcome, I'm Professor, and once again, I'm happy to be your tutor. So far, we have outlined some basic concepts, and in this lecture, we are still going to build up on the fundamentals. Now, I need you to understand that these fundamentals would go a long way to help you to better understand how electronic components and devices work the way they do. So far, some of the things that we've learned includes the fact that atoms do have unique number of protons. The number of protons is the same as the number of electrons. Protons carry positive charges, electrons carry negative charges. The charge of the proton is equal in magnitude to the charge of an electron, but they differ in sign. Also, because of the equal amount of positive and negative charges in the atom, the total positive effect of the protons is balanced by the total negative effect of the electrons, making the atom electrically neutral. Neutrons, on the other hand, we said do not have any charge. And actually, in the domain of electronics and chemical reactions, we are mostly interested in electrons because protons and neutrons do not take part of these activities. And even for the electrons, we are only interested in what we call the valence or outermost electrons. In a previous lecture, we talked about electron configuration. We said that electrons arrange themselves in shells with specific energies around the nucleus. The shells with lower energies are filled first before the shells with higher energies. According to the octet and duplet rule, elements are more stable when they have a fully filled valence shell. To achieve this, the atoms of elements tend to lose or gain electrons. And in this particular lecture, we're going to look at the various mechanisms that brings about the loss or the gain of electrons. Now, the question you are probably asking yourself is, what determines whether an element will lose or gain? Well, we know that protons do not partake in electronics, hence we cannot change the number of protons in the domain of electronics. Actually, when you change the number of protons, as can be done in nuclear physics, you are essentially creating a different element. So, to determine whether an atom will lose or gain electrons to have a fully filled valence shell, the following rules can be applied. The first is that atoms with less than 5 valence electrons will lose these valence electrons to become positively charged. The second rule is that atoms with 5 or more valence electrons will borrow or will gain extra electrons to have a fully filled valence shell. However, the hydrogen atom has a unique case. It has one electron, as we know, it is the first element, and also it obeys the duplet rule. Okay, so since the duplet rule involves shells, the valence shell having only two electrons, one, which is the only electron that hydrogen has, is actually exactly half of two, right? So in the case of hydrogen, it can actually accept or lose its valence electron. Okay, when an atom loses electrons, it becomes positively charged. I hope you know why. When an atom loses electrons, it does not lose protons, so it develops a net positive charge due to the electron proton imbalance. Now, the charge the atom acquires is equal to the number of electron lost. Therefore, when a single electron is lost, as in the case of hydrogen, the atom acquires a net positive charge. A charged atom is called an ion, and a positively charged ion is called a cation. When a hydrogen loses its electron, it becomes a proton. Probably this is the easiest way of creating a proton for any activity in physics or chemistry. Now, a positively charged hydrogen atom is called a hydrogen ion, which is represented by the symbol H+. The hydrogen atom can also gain an electron depending on the nature of the interaction. Now, since it obeys the duplet rule, it can gain up to one electron. Gaining an extra electron will render the atom negatively charged. A negatively charged ion is called an anion. A negatively charged hydrogen ion is called a hydride ion with a symbol H minus. You can refer to any good chemistry textbook for details on the naming conventions. Helium has exactly two electrons, hence naturally it has a stable electron configuration. Therefore, helium, like other noble gases, does not have a need to become stable. So, for this reason, helium and other noble gases exist as monoatomic gases. Now, a monoatomic gas is a gas whose unit constituents are atoms instead of molecules. Now, generally, noble gases have low chemical reactivity. So previously, chemists thought they were not reactive, so they used to call them inert gases. However, they do react. For instance, xenon can react with fluorine to form xenon difluoride, xenon tetrafluoride, and so on. Now, think of the noble elements as the role models of the other elements. Lithium has one valence electron, hence it will lose it to become a lithium ion, which is Li plus. After losing the electron, the electron configuration of the lithium ion becomes the same as helium, which is a noble gas. As you probably know already, lithium is used extensively in the manufacturing of batteries. Oxygen will gain two additional electrons to become negatively charged, resulting in an electron configuration like neon. Neon is the 10th element in the periodic table with an electron configuration of 2,8. Hence, like lithium, neon is a noble gas because it has its valence shell filled up. Aluminium has 13 electrons. Hence, its electron configuration is 2,8,3. Therefore, aluminium is likely to lose the three valence electrons to assume the electron configuration like that of neon. Silicon is the 14th element, hence it will lose the 4 electrons to become positively charged. A silicon ion written as Si4 plus is formed in the process. Whenever there is a loss or gain of electrons, the resulting electron configuration is that of a noble gas. The number of electrons an atom can lose or gain to become an ion is called its oxidation number or oxidation state. In the previous lecture, I touched on transition metals. I said that transition metals have multiple stable electron configuration. This means that transition metals do have multiple oxidation states. Example, copper, iron, and cobalt. The reason this happens in the case of transition metals is that they generally have their valence electrons in two shells instead of one. Take copper for instance. In the previous lecture, when we arranged electrons in copper, we ended up with this electron configuration. Well, one thing that I did not mention is that degenerate orbitals like p and d orbitals tend to have an extra stability when they are either half filled or fully filled. So, in one of the configurations of copper, an electron from the 4s orbital will jump to fully fill the 3d orbitals. Hence, in an event of ion formation, only one electron would be lost in the 4s orbital, leading to the formation of the Cu plus ion. Copper, however, may lose all the electrons in the 4s orbital, leading to the formation of Cu2 plus ion. A similar thing happens for the rest of the transition element. Now, you may be wondering, where do the electrons go when they are lost or come from when they are gained? The electron must go or come from somewhere. The process of ion formation is called ionization. The energy required to release an electron is called the ionization energy. And the energy that is released when an atom accepts an electron is called electron affinity. Atoms with higher electron affinity are likely to gain extra electrons to form negative ions. Now, Many processes can actually lead to the ionization of atoms. For instance, by the application of thermal energy. Atoms can also exchange electrons through chemical reactions, forming a chemical bond in the process. A chemical bond is formed when it is energetically favorable. That is, when the energy of the bonded atoms is less than the energies of the separated atoms. You see, nature is economical. This is because nature always wants to assume configurations with minimum energy. There are three primary types of bonding. We have ionic bonding, covalent bonding, and metallic bonding. Ionic bond occurs when one atom donates electrons to another so that each of them end up with a fully filled valence shell. For instance, sodium, which is the 11th element with an electron configuration of 281, can lose its single valence electron to attain a fully filled valence shell, according to the octet rule. Chlorine has 17 electrons with an electron configuration of 287. Chlorine has the affinity to accept an electron to have a fully filled valence shell. So sodium can donate its electron to chlorine so that both of them get bounded together as sodium chloride. Sodium chloride is much more stable than the elements themselves. Now, this is a typical example of ionic bond. Covalent bonds, as can be broken down as covalent bonds, take on a different form. It involves sharing of what we call electron pairs. Now, in a covalent bond, two or more adjacent atoms may pair up their valence electrons to create 8 valence electrons for each of them. This results in a state of chemical stability. However, the shared electrons are not mobile, they become localized. Take silicon for instance. Each silicon atom has 4 valence electrons. Hence, in a silicon crystal, each silicon atom bonds covalently with neighboring atoms, leading to 8 electrons. Now, each atom in the covalent bond behaves as if it owns all the electrons. Metallic bond occurs in metals. Metals are solid at room temperature. Take copper for instance. The valence electrons of most metals are loosely bound to their parent atoms. So at room temperature, that is about 25 degrees Celsius, the thermal energy available is enough to cause the valence electrons to break loose from their parent atom and move through the confines of the crystal or the element. This creates a sea of valence electrons that are not associated with any particular atom. Now, the parent atoms become ionized due to the breaking away of the valence electrons. The ionized parent atoms are what we call the ion cores. The sea of negatively charged valence electrons hold the positive ion cores together in a metal, and this is how metallic bonds are formed. The valence electrons determine most of the properties of materials, such as their electrical and thermal conductivity, the strength of the material, etc. We shall look at applications of these things later in the course. Alright, that is all for this lecture. In the next lecture, we shall briefly look at the properties of some materials. We will look at the tungsten metal, nichrome, copper, aluminium, silver, gold, and mica. Once again, I am Professor. Thank you for watching.